All right, for this we're going to look at a very standard case of dealing with motion involving an acceleration. So here we have an eagle that's diving out of the air. You have the initial velocity of the eagle. It says speed there, but it's a velocity. It has a direction. And you're told that the acceleration that it experiences throughout its entire flight of motion is 9.8 meters per second squared down. And what you're told is it starts 100 meters above the ground, and what you want to figure out is how long will it take to reach the ground. And lastly, at what speed will it be traveling at when it reaches the ground. Now, in order to solve this, what you want to do is you want to take a look at your two characteristic vector style equations that solve problems involving motion that you can see with accelerations. Now, there are two equations here. However, both of them use a combination of several variables. Both of them use a velocity, initial and final. Both of them use a displacement, and they can also use an acceleration. So the very first thing that you're going to want to do whenever you have one of these problems is, first of all, you're going to want to take a look at your problem and take a look at the things that you've been given. So you've been provided with an initial velocity. You know it's initial because you're told that. You know, you know that there's an acceleration. And you know how far it has moved downward. What's important to note here is you don't actually know how far it's moved left and right. So with this, you can actually start filling in these quantities. So we'll start off with displacement. Your bird starts off over here, 100 meters above the ground, and you're looking for it when it reaches the ground. So it goes from 100 meters up to the ground. The very first thing that you can do is you can figure out its displacement. Now, it's important to note here that you don't actually know how far it's moved horizontally. All you know is how far it's fallen. This straight downward could be an option. You could also have an option in which your bird does something like this, because all you know is the vertical part of your displacement. Now, when you find your displacement, though, because we're doing math, we're going to want it in Cartesian form. So the question is, how do we deal with these Cartesian components? Well, we don't know how far it's gone horizontally. All we know is how far it fell. So for the horizontal part of my displacement, I'm just going to put a variable x in its place. This is just going to serve as a placeholder for this part of the displacement. As for the vertical part, I know that my eagle is going 100 meters downwards. So we'll leave the units out, but for the vertical part of my displacement, I will have negative 100. And that's the first vector quantity put into place. I can then work my way through. We can take a look at the acceleration. For this acceleration, I'm actually told quite explicitly what it is. I've been told that it is 9.8 meters per second squared straight downward. If it's straight downward, it's not going to have any horizontal motion. And for its vertical motion, it is downward. So I'm going to take negative as being downward, like I did for the displacement. And as for the value, we're going to use 9.8. Again, the units here are meters per second squared, but we'll leave those out for now. Now, if I take a look at the last thing that I've been provided with initial velocity, just initial velocity. And I've been provided with the entire vector for it. But what I'm going to want to do in order to make my math as simple as possible is I'm going to want to put this into Cartesian notation. So what you can do is you can take a Cartesian xy plane. You can draw your initial velocity. It is to the right and upwards, like so. If you take a look at how the direction is written, right shows up first. So my angle is going to be touching the right side. This angle is pi by 6 radians. And I've been told the hypotenuse here, which is 25. Now, this is not in the most pleasant form in the world, so what I'm going to want to do is I'm going to want to turn this into a right angle triangle with an x part and a y part, which are these two parts that are in purple here. So we'll just call them x and y. This is different than the x that's present in the displacement. Now, I can use trigonometry here. How you do so is up to you. But for me, I would use sine and cosine. I would use the cosine of 25 is equal to, or sorry, the cosine of pi by 6 is equal to x over 25. So the cosine of pi by 6 is equal to x over 25 because cosine is adjacent over hypotenuse. And if you work your way through for x, you get x is 21.7. And I can use sine of pi by 6 is equal to y over 25 because sine utilizes the opposite side in the hypotenuse. I can then solve this and I'll get 12.5. It's important to note here that I am working in radians because there is no unit associated with my angle. Now, with this out of the way, I can actually fill in my initial velocity. So for my initial velocity, which is v naught, or v subscript 0, the x part of it is 21.7, positive because we're going to the right, and the y part is 12.5, positive because we're going upwards. And with that, all my vectors that I've been provided with are processed in a nice, convenient form. All right, so that should be the first step of what you're dealing with. You're literally taking everything you've been provided with and you're rewriting them so that they're in a form that is convenient to use. That form is always Cartesian form. Now, with that being said, we can start doing our mathematics. If we take a look at these two equations here, we have a bunch of variables that we don't know. If I take a look at this top one, I do know what v final is. I don't know what v naught is. Right, so I don't know this, and I don't know delta t. So this top equation I actually can't use as it's written because it's got two variables in it that I don't know. If I take a look at this bottom one, though, I can do some work with this because even though I don't know the total displacement, I know a little bit about the displacement. I know a little bit about I know the initial velocity. I just don't know the change in time. And I know the acceleration. So what I'm going to do here is I'm going to take this equation and I'm going to write it out. Now, I write things out with full vectors. You don't have to. But basically, for my displacement, I have x negative 100. This is equal to the initial velocity, which is 21.7, 12.5, multiplied by the change in time. I'm just going to use t here, plus 1/2, or 0.5, multiplied by the acceleration, times t squared. So this gives me an equation with which I can work with. Now, if you take a look at this, what you will notice is there's both x parts and y parts. As we discussed before, the x and y parts are completely separate. So what you can actually do here is you can take a look at all the x parts. 1, 2, 3 of each of your vector quantities, and you can write them into a single equation because, again, they're completely separable. So here we have x is equal to 21.7t plus 0.5 times 0 is 0, so there's nothing left here. I can do the same thing with the y parts. I have negative 100, 12.5, and negative 9.8. So if I write these all out with the y parts, I can do negative 100 is equal to 12.5 t plus, or I guess in this case, minus 4.9 t squared. The reason we get negative 4.9 here is we're taking 0.5 and we're multiplying it by negative 9.8. When you do this, you can take a look at these two equations. It is actually possible for me to use this green one here and solve for t. Now, this green one here involves a quadratic equation. This is a skill you need to be able to possess, so if you're not familiar with how to do this, please go back and review some of the previous tutorial week 0 lessons. Now, if you solve this, I recommend you use a quadratic formula. You will get two answers here. The first answer you'll get will be negative 3.42 seconds, and the second answer that you will receive from this quadratic is 5.97 seconds. Now, whenever you do a quadratic, you will, more often than not, get two possible solutions, so you need to figure out which one's right. One thing I will tell you is We didn't travel backwards in time. Right, and that's what the negative time solution represents. It represents a hypothetical solution that allows for you to basically time travel. Because that doesn't happen, we can use this to find t. And this is actually the first thing that we're being asked for. We were asked specifically how long would it take to reach the ground. Right, so with this determined, we're basically finished. You could use this t to find x if you like to complete your displacement, but it's not necessary here. Now, for the second part of this problem, we're going to hold on to this t that we have because we went to all the work to solve it. We might as well not get rid of it. The second thing we've been asked to find is what speed will it be traveling when it reaches the ground. So to do this, we're going to find the final velocity it has when it reaches the ground, and then the magnitude of that is going to be our speed. So if this is our goal, to find the speed that it'll be traveling at when it reaches the ground, we're going to find our v final, or our final velocity. Now, for this final velocity, which our goal here is to find, we actually have all the vector quantities and all the time quantities that we need to do this. We can start off with our initial velocity, which is 21.7, 12.5, and so to the right and upwards. And to this we can add the acceleration, which we have. And we now know that the change in time that we need is 5.97 seconds. This allows us to actually solve this very quickly. Order of operations still applies here. So we're going to do the multiplication first. 0 times 5.97 is 0. And negative 9.8 times 5.97 comes out to about negative 58.5, like so. We can then add these two things together. 21.7 plus 0 is just 21.7, and 12.5 minus 58.5 is around 46. It's 46.0 if you want to maintain significant figures. And this will, of course, end up being in meters per second. Now, well, hang on. Minus. There we go. I missed a minus sign. Now, with this being said, we can do a quick sanity check here. Our bird was going to the right, and it's getting pulled down by gravity. It should probably still be going to the right. So the x part of our final velocity checks out. As for the falling part, when something falls out of the air and strikes the ground, at some point it should be traveling downwards. Therefore, our y component should be negative. So with this being said, minus me for getting the minus sign in the first place, a quick sanity check is your best friend here. Now, in order to find the speed, which is the magnitude of the final velocity, we're going to use the Pythagorean theorem. So we're going to do v final squared is equal to the x part squared plus the y part squared. And again, when you're using the Pythagorean theorem, there's absolutely no need for you to include the signs. Now, you can do this fairly quickly. Just take 21.7 squared, add that to 46 squared, and then take the square root, and you'll get around 50.9 meters per second for the speed, or the magnitude of the velocity. And this general procedure is pretty much how every one of these problems involving motion that you can see is solved. The two equations highlighted in the black box, they solve every single equation that you can be asked to deal with, so long as you're able to utilize vectors.